All right, so we'll get started. So this is MSE 498, and so if anyone's not in this class, please vacate your computers because we do need all of them. Do you have a question? So that's the admin to help you out, so the guy at the desk out there. Okay, so let me pass around the attendance sheet. Okay, so just a couple of announcements. So you should have all received an email, I think, from me saying that I posted a new announcement. Is that true? Do you get an email when I post an announcement to Compass? Okay, so if you're interested, on the Compass main page, there's just some information about some upcoming stuff that Computational Science and Engineering is putting on. So there's some events which are sort of free parallel programming courses, some training workshops, and then if you're thinking about CSE as sort of a career choice, they're starting this new thing where they're going to start inviting some folks from industry. So the first chap is going to be from Procter & Gamble to come and talk about CSE in industry. So lots of free stuff that might be interesting to some folks in the class. Okay, and so that was that. And then just to orient ourselves on the schedule, so it's now October 2nd, and so today we're going to finish up the molecular dynamics theory from last time and start talking about molecular dynamics practice. And tonight, via Compass, 11:59 p.m., do make sure to submit the quiz and the project. So quiz 2 and project 2. And so I'll be around a little bit after class if there's any last-minute questions and any of those things. Again, if Compass is being a pain, please just send it to me via email. And you'll notice on the brief this time, we're not too worried about you submitting sort of scripts and codes and stuff. It's basically just answers, numbers, citations if you look up experimental data, and some plots. So if there's any last-minute confusion about that, please do come talk to me. Okay, and so with that, let's continue our journey through molecular dynamics theory. So let me just put up this slide from last time. So this was sort of slide 13, halfway through. And so this was sort of the big picture that I was trying to convey to you. You know, what are the fundamentals of molecular dynamics? And we said there are basically 3 ingredients. And so you need an initial configuration, you need an interaction potential, and you need a way to integrate force equals mass times acceleration. So if that's all you remember about molecular dynamics, that's the most important thing to remember. And so we dug into a lot of these things. So how to generate an initial configuration, positions and velocities, how we find interaction potentials. So basically we download them from the internet because they're published, they're freely available. But what goes into an interaction potential? So understanding a little bit about how we decide how the atoms and molecules speak to one another. And then the way to integrate force equals mass times acceleration. So we said, in principle, one could do it by hand, just by stepping a numerical integration over and over again. But we have computers which are very fast to do it for us, and so we just do a numerical integration using something called the Verlet algorithm. And so we remember that there were various reasons we used the Verlet algorithm. It was super simple, but it conserves all these nice properties. Okay, and so we're going to continue. So you need a computer. I'm sorry, I'm going to have to ask you to let your computer be used by someone in the class. Okay, so where we stopped last time, we're getting through some advanced topics, and so we started talking about things like thermostats, barostats, periodic boundary conditions, and electrostatics. And so where we left off was we're just going to finish up a couple more of these advanced concepts that are going to be important in molecular dynamics simulations. Then we're going to watch some movies. Then we're going to have a 5-minute break. And then we're going to start talking about molecular dynamics practice using labs. Okay, and so are there any pressing questions from last time about any of the notes or the concepts that we covered? People are all pretty happy with what's going on. So we like F equals MA, we like thermostats and barostats. The electrostatic stuff, if you didn't get that completely, that's okay, but understanding there is a rigorous way to treat electrostatics called the Ewald algorithm is sort of an important concept. Okay, so now let's talk about something called ensemble and time averages. So if you've not taken a thermal class, this probably won't make any sense to you, but it's a very important concept. And so the concept is this. If you are in the laboratory, so you're doing one of the junior year labs, and you're doing an experiment, typically what you're taking is known as an ensemble average. So you mix up some chemicals, you perhaps are interested in, you know, the properties of a particular molecule, you're taking a spectra of that molecule, you want to look at its IR spectra, its absorbance, for example. And so when you mix up your flask, there's going to be Avogadro's number of these molecules in this flask. And so basically when you take a measurement, you're taking an average over sort of Avogadro's number of molecules, so 10 to the 23 different molecules. So that's known as sort of an ensemble average. And so at every time point, we sort of take a snapshot. The molecule number 1 exists, it looks like this. Molecule number 2 has a property that looks like this, all the way to molecule number 6.02 times 10 to the 23 looks like this. And we have an average measurement, which is known as an ensemble average. Okay, what do we do in molecular simulations? We clearly cannot simulate 10 to the 23 molecules. It's just too expensive. And so instead, we take something called a time average, which is perhaps a simpler thing to think about, which is basically we simulate one molecule for as long as we can bear on our computer, and we average the properties in time. Does that start to make sense to folks? So this concept of an ensemble is an average over multiple copies of the molecule, and a time is over one molecule, but for a really long time. And so there's something called the ergodic hypothesis, which says that both of these things are the same. It says if you take a time average for long enough, it's basically the same thing as doing an ensemble average. So why is that important? Why am I telling you this? Well, that gives us confidence that what we calculate in a simulation via a time average is actually the same thing as if you could compute in an experiment using an ensemble average. So if you're a big fan of statistical mechanics, you can take a look at these slides. If you're not, please don't look at these slides because they're terrifying. But basically, this is the sort of statistical mechanical formalism of how you take an ensemble average, and this is the formalism for how you take a time average. But if you just remember what I said in words, that's basically enough. And so the ergodic hypothesis is this. It states as time goes to infinity, the ensemble average, so the thing we would measure in an experiment, is equal to the time average, so the thing we can measure on a computer. And so that gives us confidence, and it's part of the reason folks are spending lots of money and building really big computers, that as we simulate longer and longer and longer, we believe we're doing a better and a better job of reproducing experiments. So that's the whole idea here. Okay, and so the fundamental idea is sort of that if you are able to generate a sufficiently long molecular dynamic trajectory, the intuition is sort of it explores all of the important configurations or all the important states that you would actually sample in an experimental system. So if you allow it to go for long enough, the protein or the little molecule you're interested in samples all the important stuff that you would see in an experimental system. And so, of course, the problem is that a priori, we might not know how long is long enough. So imagine you're studying a brand new molecule or a system that's sort of highly radioactive, that's not been studied in the lab, and so you don't know a priori how long is long enough. And so that's one of the big bugbears in molecular simulation. So we can do things like have an internal consistency check, that, you know, as we double the length of our simulation, our properties don't change. And so internally, we believe we've sort of converged on this time scale. But that doesn't guarantee that if we treble it or multiply it by 10 or simulate for, 100 times longer, that we'll actually see something different happen. And so that's just a little bit of a caveat. And so the practical answer is basically you simulate as long as you can stand with the computational hardware that you have. And then you always have to compare to experiment or known data to see how good of a job you're doing. So we are doing predictions in a lot of cases, and in some cases we can compare to experiments, some cases we can't. It's just the facts of life. Okay, and then for slow processes, so we had a question last time about what do you do if you are interested in processes that occur, say, longer than the time scale of microseconds or milliseconds. And so you have to use some advanced sampling techniques, which we're going to discuss right now. Okay. So basically, if all you remember is this part, ergodic hypothesis, if I simulate long enough, I can reproduce experimental results. That's sort of what I want you to take home here. Okay, so how can we go beyond S equals MA? So hardware limits the sort of attainable timescales in molecular simulations, typically to sort of microseconds, or if you're David Shaw, perhaps milliseconds. And we said that the fundamental limitation is that we can't make too big of an error at every time step, meaning we have to have a sufficiently small time step, typically a femtosecond, in order to have a sort of robust numerical integration that's not going to explode or go crazy. And so if we're limited to femtoseconds, that's sort of 10 to the minus 15. And so that's going to provide sort of the hard limit on how long you can simulate. And so that's where this limit comes from. Okay, so what happens if we're interested in things that happen on timescales longer than microseconds? So basically, another way of thinking about this is that the system is perhaps trapped behind some energetic barriers, and it basically requires the order of a microsecond for a random fluctuation to take the system over the barrier to sample some new state. And so we're sort of kinetically trapped. So that's a word you'll hear a lot in molecular simulation. We're kinetically trapped. So how do we encourage the system to do a better job of sampling all the space without just sort of waiting forever and ever for our simulation to suddenly do it? And so, okay, so the fundamental idea is that we can use accelerated sampling techniques which artificially bias the simulation in order to do a better job of sampling all the important configurations or all of the important states we think are important. And so this is just a list of some of them. And so some of the most frequently used ones we sort of use all the time in my group and various other groups around the country is known as sort of umbrella sampling. And so this is a very simple technique that basically you take your molecule or your crystal and you apply some external force to it to sort of force it to sample other configurations. So maybe you're waiting for a defect to hop in a crystal. And so what you can do is actually apply an artificial potential to force the defect to hop very quickly. And then afterwards, when you do a post-mortem analysis of your simulation trajectory, you can subtract out the effects of your artificial potential. And so that allows you to actually get proper thermodynamics, but you actually sacrifice the dynamics. And so you no longer sort of believe the dynamics, but you do believe the thermodynamics. So the free energies and all that sort of stuff you can get out of your system. And so all of these really, you have to sacrifice dynamical information, but you can get thermodynamical information. So if that's what you're interested in, sort of relative free energies or entropies, these will all do a good job for you. You can also use replica exchange. So one of the simplest things you can do in the lab, if your experiment is going too slowly, is elevate the temperature. And so that can make things happen a lot faster. And so there's sort of a rule of thumb from the Arrhenius equation that if you increase the temperature by like 10 Kelvin, you get like a doubling in rate. Just a standard trick folks use in the experimental lab for a rule of thumb. It's a similar idea here, that you can actually use high temperatures to make your simulations go faster, and then you can sort of subtract out the effect of that temperature increase to try and get better thermodynamically converged results. Okay, so there are a few others here. There are things called hyperdynamics or metadynamics, which basically uses special potentials to encourage your system to widely explore configurational space. And so if you're interested in any of these are sort of the keywords to look up, and I'd be happy to talk to you about them in more detail if that's something you're interested in using in your own research. Okay, so there are a couple of other special MD variants I just want you to make you aware of, and these are not things that we're going to use, but you may use them in your own research, and it's important for you to understand that these things exist. And so this one's really cool, and so this is Carr-Parnello molecular dynamics, and so Roberto Carr and Michel Parnello said, what about if we can do molecular dynamics without having a force field? And so we said that one of the very important ingredients is this force field. We need to know how the atoms interact with one another in order to simulate the dynamics of the system, the evolution of the system. And so they said, well, why don't we actually just compute the forces using density functional theory? So use quantum mechanics to figure out how the atoms are going to interact with one another, and then use that as our force field. So at every time step, we can on the fly compute the interaction between the atoms using quantum mechanics, and then use that to make one step in our integration algorithm, to integrate F equals MA for one time step. Then you can use quantum mechanics to, again, recompute all the forces and sort of rinse and repeat and just go round and round like that. So the underlying force field is basically computed on the fly using quantum mechanics, and you feed that to a molecular dynamics algorithm that then steps you forward in time. And so what's the advantage here? Well, we don't need any force field, so we don't need to do any of the sort of parameterization tricks. So we believe that, the force fields are pretty good. But at the end of the day, we're forgetting about electrons. And so if electrons are important, if you're looking at sort of activated processes or photon absorption, the electrons are going to play a big role. And so this allows you a way to explicitly incorporate them into a molecular dynamics algorithm. Okay, so what's the penalty? It's very, very expensive. So at every time step, you have to do a quantum mechanical calculation to get the forces. And so that slows you down a lot. And so you're only going to be able to reach maybe nanoseconds on really big computers. And so you can't hit the time and length scales you can attain with standard molecular dynamics using classical potentials. Okay, so one thing molecular dynamics is really bad at, because we forget about the electrons, is chemical reactions. And so if you forget about the electrons, you can't do any chemical reactions. And so if you do a molecular dynamics simulation, you're never going to see bonds forming and breaking because we're using purely classical potentials. And so there's a way to fix it up. So one way is to explicitly incorporate the electrons. A slightly more coarse way of doing it is to have special molecular dynamics force fields known as reactive force fields. And so these are basically some sort of intermediate between quantum mechanics and purely classical. There's some sort of hybrid in between that, uses some sort of cheating techniques to basically simulate bond making and breaking. So perhaps you simulate using your fancy react FF force field, and if two atoms get close enough, maybe they then form a bond. Or if they become energetically excited enough, maybe they break the bond. So it's a way of actually doing chemistry inside a molecular dynamics simulation. And so these force fields are sort of less mature than the standard ones. We will use like the EAMs and the MEMS, and so you have to be a little bit careful with using them, but they do exist. Okay, so a couple other ones. GPU-enabled molecular dynamics. So just like Quantum Espresso has recently been developed to run on GPUs, you can run molecular dynamics codes like LAMMPS and GROMACS on GPUs. So if you have an old PlayStation at home that's start collecting dust, you can actually use the graphics processor on that PlayStation to run molecular dynamics simulations. And so in my group, some of the workstations we buy for my graduate students are actually these like Alienware machines for gamers. And so they come with like all these crazy flashing lights, and like you get a free baseball hat and like a speaker that you can use to talk to your friends over the internet. And so we have a hard time buying these because the purchasing department gives us trouble, and we say, no, we're not actually using them to shoot aliens, we're using them for molecular dynamics. And so they have very fast graphics cards that we use to do molecular dynamics simulations. And then the other thing is implicit field models. So we talked about this a little bit, that if you have a really big system and you don't want to burn a lot of CPU cycles simulating all of the water molecules or all of the methanol molecules that solvate your system, perhaps you can use some sort of implicit model, so basically solving Platon-Boltzmann electrostatics or something like that. So you don't have to explicitly have all of your solvent molecules, you just have your solute that you care about, and then some sort of implicit force field that mimics the effects of the solvent. Okay, so just to make you aware that there are some fancier AMD things that are available if you need them. Okay, so then just a couple of slides on limitations and common mistakes. So how is my molecular dynamic simulation going to most commonly break, and what cannot it do? Okay, so it can't do chemical reactions very well because there are no electrons, but we said you can use reacts-FF to reactive force fields. We can't do quantum effects, but if you really need them, you can do hybrid quantum mechanics, molecular mechanics using Carr-Parrinello ab initio molecular dynamics. Force fields may work really well at this state point for which they were parameterized. So if you have a force field that someone has developed for 298 Kelvin and 1 bar, maybe it works really well there. If you're interested in sort of a diamond anvil cell with sort of super high pressures, maybe your force field's not going to work so well. Maybe it's not being tested up there. In a sense, it's not adaptable or transferable. And so you have to be very careful when you use a force field out with the range of its applicability. It might work okay, it might not. Fundamentally, you don't know. And so typically you have to validate it against experiments or perhaps more advanced calculations like quantum mechanical calculations to give you confidence that you're going to get reasonable answers. Time and length scale limitations. If you want to simulate a chunk of metal that's sort of 1 meter long for 3 months, you're not going to use molecular dynamics. So just being aware of where we are on that time and length scale diagram. We can hit sort of nanoseconds to maybe microseconds, milliseconds, over length scales of perhaps sort of several tens of nanometers perhaps. And so just being aware that you have to use the right tool for the job. And then we talked about the statistical significance of our trajectories. So we managed to get time on blue waters for 1 month, and we run one single enormous trajectory of defect hopping in aluminum. How representative is that trajectory? Because we only have one. Would it have been a better use of our time to perhaps run 10 shorter trajectories and take the average over them? So just being aware how significant is just one molecular dynamics run. And then finally, and this is sort of the biggest thing, are you equilibrated? So have you run long enough such that your system has sort of relaxed from its initial state, that may be a completely wrong state that the system would never naturally explore, to start sampling the equilibrium states that you would see in an experiment. And so we need to spend sort of the first little chunk, and little chunk can mean different things in different contexts, of your simulation waiting for the system to equilibrate, and then you can start sampling quantities and making some molecular dynamics predictions for dynamics and thermodynamics. So it started the same way in our quantum espresso calculations, that we had to guess a bond length and then we had to relax the system, and only once we'd relaxed it were we start confident we could make some decent predictions. It's the same thing here. You start your system with a crystal, perhaps it's got some solvent around it. Maybe that's a really bad starting configuration. So you have to burn some CPU cycles to let the system relax to a certain natural state, and then you can start collecting data. Okay, so this is sort of an important slide which is going to lead into what we're going to start talking about, which is the practice of molecular simulation. So what are the common mistakes? So what are the big errors folks make, myself included, when they're doing molecular simulations? So the number one problem is the simulation is too short. So you do a simulation of something, you get some very nice converged answers, and you're very excitedly run down the hallway to your experimental collaborator, and they're just in complete disagreement. And so what they find from experiment does not agree whatsoever with what you found from simulation. So the first thing that should come to your mind is maybe I didn't simulate long enough. Maybe I just need to wait longer for my system to equilibrate. Maybe these are processes that are happening on much longer timescales than I can actually simulate. And so the things you can compute from a 1 nanosecond simulation are not really relevant to the things that happen in the laboratory on the timescale of minutes or hours. And so being very aware that we are restricted stringently in time and length scales, and so we may be too short. Another big one is inadequate force field. So garbage in, garbage out. If you have a terrible force field, or you have a force field that's not sort of applicable at the state point you're interested in, you're not going to be able to trust the results. So typically you want to use well-validated force fields within their sort of range of applicability, and even better if you can compare to some experimental data that will give you confidence in further predictions you can make with your molecular dynamics. We got too greedy. So delta T was too large. So the time step we wanted to take was too big. It was bigger than sort of 1 or 2 femtoseconds. And so that means we're sort of accruing all sorts of errors in our molecular simulation, and our trajectory, our numerical integration trajectory is basically unstable. And so we think we're integrating F equals MA, but really we're just accumulating errors. And so the noise sort of overwhelms the signal. So don't get too greedy with your delta T. It's very tempting because, you know, doubling delta T allows you to then double the maximum time you can simulate, but you've got to be careful about error control. System is too small, so that's very similar to simulation was too short. And so maybe the effects that you're seeing in the laboratory are actually sort of cooperative events between tens or hundreds of molecules, and if you can't simulate tens or hundreds of molecules, or equivalently for crystals, if you're simulating insufficient chunk of your crystal, then you're not going to be able to see the effects that you might see in a lab. Another one, missing important physics or chemistry. So you think you're simulating a system that's sort of perfectly aligned with what's being studied in the lab, but maybe actually in the lab the impurities are very important, or the particular salt that they use is very important, or the pH is really important. And these were things you didn't account for, or didn't bargain for when you were setting up your simulation. So you're going to get an answer for the thing that you simulate. And if you're simply missing an important piece of your system, you're not going to get the correct answer. So understanding that limitation is sort of subtle, but it's very important. And then a more technical one, your cutoffs are too short. So we said that you have to have a particular cutoff for your Leonard-Jones interaction and for your Coulomb interaction. And if that's too short, maybe again, you're actually introducing artifacts into your simulation and your predictions are going to be wrong. So making sure that your cutoffs are sufficiently big. Okay, and so that was the end of sort of more advanced concepts in molecular simulation. So does anyone have any questions about anything so far? Okay, so let's look at some packages, and then let's look at some applications and movies. And so these are sort of again, thinking of these notes as sort of a library for you. These are the popular molecular dynamics software packages. The one we're going to be using is called LAMPS, and so it comes out of Sandia National Labs, and it's free. If you're doing molecular simulations, so I should say, if you're doing LAMPS, it's really good for condensed phases, so solid systems, crystals, metals, semiconductors, things like that. LAMPS is probably your package of choice. If you're interested in proteins and biomolecules and DNA, you may want to use something like GROMACS, CHARM, AMBER, NAMD, or DE-Shaw's package. And so these things are all more geared towards biological stuff. LAMPS is typically more geared towards materials stuff. And so it just depends what you're interested in. So each package can do the other. It's just more convenient to do materials, metals, stuff like that in labs, and biomolecules in these guys. HUMD Blue is a really interesting code. It runs exclusively on GPUs, and so most of these codes have some GPU functionality. HUMD Blue exists entirely on the GPU, so it doesn't do anything on the CPU, which means it's sort of lightning fast for certain systems. The penalty you sort of pay is that there's limited memory on a GPU card. So typically you can't simulate really, really big systems because you just can't fit them on the GPU card memory. But for things containing sort of several tens of thousands of atoms, you can typically do that on a GPU card in modern machines. So that's a nice one to bear in mind. And then there's this other interesting package which comes out of Stanford, so Vijay Pandey's lab. And if you're familiar with this, do you remember the SETI stuff where you could use screensavers to search for like extraterrestrial life? And so if you have spare cycles on your computer, you can like download a client to like process signals that come in a large array in New Mexico. So Vijay Pandey is using this idea to actually fold proteins. And so you can download his little client, and it uses your spare CPU cycles to actually do a little bit of a molecular dynamics simulation and figure out how proteins fold. And so it's like a distributed computing all across the world, and each little computer, although quite, sort of weak on its own, when you combine them together, they can actually be quite powerful. And so I think he has like several petaflops of CPU power now under this distributed computing umbrella. So if you're interested, you can go to his website and you can actually download it for your own machine. And they have sort of cool graphics and stuff that you can watch the protein you're actually folding happen on your screen. Okay, so some packages. The one we're most interested in is LAMP. Okay, so let's look at some applications. So some of these are movies. And so we're actually going to do this. And so one place in materials engineering that, like the dynamic simulation is used a lot, is in fracture mechanics. And so you can build a crystal, and this crystal contains a bunch of atoms. You can introduce some defects, and then you can pull on the crystal and watch how crack propagates, or how the material will fail. And so that's kind of interesting because it can give you sort of atom-level insight into how materials might fail or might not fail. So for instance, crack propagation. So we've introduced an external crack here. We're going to yank on the top and the bottom, and we're going to watch how the crack propagates. And then you can start thinking about, well, how is this affected by which crystal plane the crack exists in? How is it impacted by the presence of defects? How does pressure or temperature change how the crack propagates? So lots of interesting materials engineering questions that you can really get atomistic resolution on. Phase transitions. And so what I'm showing you here is a bunch of liquid silicon. We drop the temperature, and you can actually watch this thing crystallize. And so this is sort of remarkable, that this perfect crystal structure emerges out of the chaos of the liquid. And this is a function of the force field. And so obviously the force field was built such that silicon likes to be in a particular configuration at low temperatures. And so when you run your simulation, you might start very disordered, but then you're sucking energy out of the system basically and reducing it to its, where the crystal is favored over the liquid, and you can see this thing fall into this beautiful lattice arrangement. And so maybe this is interesting because you want to see again how impurities affect crystallization, or maybe you want to see how admixtures, sort of adding two different materials together, can you change the melting point of your system? And of course, very important considerations when you're designing materials for sort of difficult environments. So high temperatures, perhaps there's radioactivity involved, perhaps there's strong mechanical stresses. Okay, so liquids, and so we actually saw this a little bit in the movie we watched last time, which was that we can predict structural properties of the liquid. So you remember we had this weird thing called the radial distribution function, which basically says, say we're in water, if I tag a particular water molecule, what is the distribution of other water molecules around me? And so we got this sort of nice curve that shows sort of the first solvation shell, the second solvation shell. And so you can make pictures like this. And so this might be a drug molecule, and you're interested as to how it lives in water. And so you can look at how the water is structured around the drug molecule, and that might have very important implications for its activity. And so you can make sort of very detailed molecular picture of how molecules are interacting. Okay, so let's look at a couple movies. So the first one we're going to look at comes actually from the University of Illinois, so from Klaus Schulten's lab. So this is KS is Klaus Schulten at uiuc.edu. So he's in the biophysics department. So he has his lab up in Beckman, and they have some enormous computers in which they do sort of crazy simulations of very, very large systems. One of the most recent ones, they did the HIV virus, and so the cat sit inside the HIV virus. It had like millions of atoms, and they used blue waters to actually simulate how that thing looks and some small portion of its dynamics. So the one we're going to look at today is ion conduction through a silicon nanopore. And so silicon nanopores are sort of interesting because you want to maybe use them for membrane separations or reverse osmosis or things like this. And so we'd like to understand at the atomistic level how ions are actually transported through these things, and then how might we engineer them to be even better. And so we're going to show you a nice movie of that. Okay, so this is the nanopore, and then they have some beautiful visualization software also. So yellow is silicon, and red is oxygen. And then we're solvating it, so that's water, and then we got a bunch of little ions moving around in the water. And so there's a concentration difference over the silicon nanopore, which is a net driving force to push ions through. And so you can watch the ions actually being conducted through the pore. And so interesting questions you might ask, how does the current depend on the size of the pore? How does it depend on the concentration gradient? How can I engineer my pore to be more efficient? How can I engineer my pore to only allow the conduction of particular ions and reject the conduction of other ions? So lots of really interesting molecular level engineering and understanding you can gain from MD simulation. Okay, so the next one is from Vijay Pandey's lab. And so this one has music, which is cool. And so I believe it was also done with the folding at home distributed computing server. And so they were interested in how this particular protein folds. And so it's the NTL9 residues 1 to 39. It's a standard sort of test case protein for folding. And so we're going to see it fold into its final structure, which looks something like this, starting from an unfolded state. And so you can imagine this is very interesting if you want to try and design drugs or figure out how enzymes work, or how molecules bind to cell surface receptors. You need to know the 3D structure of the protein. And so if we can predict that using computers, that's sort of a very important fundamental understanding, sort of scientifically, and for rational engineering of sort of drugs and therapies. So it's a big industry, protein folding, and we're going to watch one of these things fold in real time. Oh, hold on, let me fix the sign. The sign's very important. Okay. Okay, so that's about as exciting as molecular simulations are ever going to get. So the story was he had made this movie, and he was about to sort of publish it and put it online, and he showed it to one of his colleagues. And one of his colleagues says, you spent all this computational time and effort actually making this movie, but it's really boring. Why don't you add some music to it? And so he said, aha. So that's where that came from. Okay, so it's, the link is down here if you want to watch it at home. Okay, so that's it for the theory of molecular dynamic simulation. So are there any questions on anything we've covered? Okay, so I propose we sort of take a couple minutes break, grab some water, stretch your legs, and then when we come back, we'll talk about the sort of practice, so actually using labs to do things like this. Great.